In this example, we are going to use a table to evaluate composition functions. In the table, for given x values, we can see the output of both the function f and the function g. For our first example, we are looking at f of g. This notation here with an O, what looks like an O in the middle, doesn't mean multiplication. It means f of g, the function g is being plugged in, and instead of x, they're telling us to evaluate this at the point 1. So we'll start with the innermost part of the parentheses, g of 1. So I'm looking at the table and I'm looking at when x is equal to 1 and the output for g is 0. So this is now going to be f of 0. Then I'm going to go to the table and see when x is equal to 0, and I see that the output for f is equal to 5. So this is our answer for the first one. Let's move to the second one. This is the same as g of f of 2. So I want to first figure out when x is equal to 2, the output for f is 1. So now I'll rewrite this as g of 1. And then I go back to the table and I look at when x is equal to 1, g is equal to 0. So this is 0. For the third example, we're using the function f twice. So this is f of 3. Starting on the inside here, when x is equal to 3, the output is -1. And then when I go to -1, the output of f is 7. Let's do a different set of examples that are related. For these examples, we're instead going to be using a graph. So this would be figuring out what the output looks like if we take one function and plug it into the other. For example A, I'm going to start with the function f, and I want to know when I plug 1 into the function, what is its output value? Well, when x is equal to 1, it looks like y is equal to 1. So the output is 1. So this is going to be the same as g of 1. Then I'll move over to the function g, and when I plug 1 into the function g, I also get an output of 1. So this example gives me 1 as the answer. For example 2, I want to start with function f and plug 2 in. The output for 2 is equal to 4. So this is evaluating g of 4. Then I move over to the second graph. When I plug 4 into the original, I'm getting 2 back. This is because the two functions that I have are x squared over there on the left and the square root of x on the right. And so when I'm plugging the functions, those points back and forth, it's like I'm taking inverses of one another. What if I start on the right-hand side? What if I start with g? When I plug 1 into the function, I get 1. And when I go to f and I plug 1 into the function, I also get 1. So look at this example and look at this example. I have g of f and I also have f of g, and I'm getting the same output. When we get the same output like that, that's the definition of inverse functions. All right, for our last example here, we're looking at f of g of 4. So I'm starting with the function g. When I plug 4 in, I get 2 as the output. And as you would suspect, when I plug 2 into function f, I get 4 as the output. So whatever I started with that I was plugging in, which in this case was 4, I'm ending up with that as the answer because these are inverses of one another. For our last example for this video, we're going to use the same process of evaluating a composition function at a particular point, but now using just the formulas. So let's do a little bit of work here. I'm going to start by evaluating g of 2. I'm going to do some side work over here. G of 2, I'm going to plug 2 in. I'll get 3 times 2 plus 5, which is 11. All right, so that means that what I'm actually trying to do is take f of 11. Now I'll plug 11 into f, and I'll have 2 times 11 squared plus 1. This is 2 times 121 plus 1. Let's see, that's 242 plus 1, or, let me move this down, 243. Let's do another example. So I'm going to start by thinking about that inner function. So for my side work, I want to find f of negative 3. That'll be 2 times negative 3 squared plus 1, which is 2 times 9, or, oops, this should be a plus, 19. So for this, I'm plugging 19 into g. So this will be 3 times 19 plus 5. 57 plus 5 is 62.